Let's try and use a transistor as an amplifier using a simple circuit shown on the screen. Also shown is a sine wave with which the circuit is fed. When the signal is at point A, that is 0 volts, then no current is flowing into the base of a transistor. IC is equal to beta times IB, as we've learned before, and since IB equals 0, this means that IC equals to 0. So there is no voltage across the collector resistor, because this voltage is equal to IC times the collector resistance, and IC is equal to 0. So we have a situation which is shown on the diagram on the screen. Since VCC is 10 volts, that is the positive supply, and there's no voltage across the resistor, the output voltage, which is the supply voltage minus the voltage across the resistor, is equal to 10 volts. Next we have a situation at point B on the input sine wave shown. Now we have a voltage, which means that the input base current is not equal to 0. And that means that IC is also not equal to 0. Let's say, just for the sake of example, that this results in a collector current of 1 milliamp. The result of this is shown on the screen. As you can see, this results in an output voltage of 9 volts. At point C, the input is even larger, and so therefore is IC. Let's say, as an example, it's now 2 milliamps. So now we have an output voltage of 8 volts. At point D, we're back down again to 0. So again, Vout is equal to 10 volts, which was the case in point A. At point E, the base emitter diode is off, it's reverse biased, and so IC is equal to 0 and Vout is equal to 10 volts. So plotting all these output points on a graph, we have a waveform that looks as shown in the diagram on the screen. This is obviously not a very good amplifier because half the waveform is missing. So if it were, for example, amplifying an audio signal, it would sound very distorted indeed. We'll look in the next video at what the answer is.